This video wraps up our principal component analysis unit, and what I want to do is just go over the results from lab number 2 and help you a little bit with interpreting what you've seen there. And this assumes that you actually have done lab 2. So if you haven't done it yet, work your way through it. These are the links to the lab and the data that you need to do the lab. And then once you have it and thought about it yourself, then watch this video and get my take on what the results mean. So let's go briefly over the principal component analysis example from the lab, and I just walk you through it and give you some hints to interpret it so that you get a good start with that first lab. So we've been working with this US arrests data here, and if we look at that data table, it's essentially crime statistics, number of murders, assaults, and rape, and we also have the urban population percentage, and these are presumably incidents per 100,000 or something like that. So this is one of the built-in data sets in R, and one of the nice things is that it's already well prepared, so our row names are actually not part of the data set. It's not a proper variable here. So that's nice. We can feed that directly into a principal component analysis, so that entire data table here can be run. We don't have to select particular columns. So we set the correlation matrix as true because these were at different scales, as you can see here. So the numbers are quite different, but for the moment I think I'd like these variables to be all equally weighted. So we use the correlation matrix instead of the covariance matrix. So let's run this, and we can get our biplot, which summarizes our original variables, just like I explained this in the previous videos. So we can see here that we have component 1 representing murder, assault, and rape. So that can actually be summarized into a crime component. So component 1 really is something that could be described as a new factor. We can call that crime. And then the interesting thing, the urban population, percentage of urban population, is actually at a right angle here. So it's not very much related to crime, maybe slightly, but not very strongly. So my urban population is primarily reflected in component 2. So those two components here, they are orthogonal. They have nothing to do with each other. So you can also say they're at right angles. And also my vectors that are at right angles, those have nothing to do with each other. So urban population is completely independent from murder. And it's also pretty independent from assault, maybe slightly associated with the number of rapes. So it's a nice summary. And the key insight from such a plot here lies often in the vectors that are orthogonal to each other, so that don't have anything to do with each other. So if I were to say, oh, what did we learn from this analysis? It's that the urbanization doesn't actually necessarily have to do anything with the rates of murder and assault. So that's interesting. So not necessarily what you expect. And the other thing that I should mention when interpreting these vectors here, you can think of those vectors like axes. So if I was to ask which of my states has a component value of minus 0.2, it would be all these here, right? So Vermont, North Dakota, New Hampshire, and so on. So the ones that are on the very left here. And these axes should be interpreted similarly. So everything that's perpendicular to this is expected to have that high value. So if I were to ask which ones have the highest murder rate, I would look at this set here that's perpendicular to that murder vector. So that would include Mississippi, North Carolina, South Carolina, Florida, and so on. And the other thing you have to keep in mind, that that vector always originates from the zero, from the origin, but the other side has equal meaning, right? So the scale extends in the other direction. So if I want to know which ones are my states with the lowest murder rates, those would be here. Wisconsin, but also Connecticut, Rhode Island, and up here Vermont, West Virginia. So they all are on that very left side, perpendicular to that murder axis. Good, so let's take a look at our summary statistics. So what's important here are these numbers. This is a proportion of the variance explained. And so my component 1 explains 62%. So that's this component here. My second component explains a quarter of the variation. And you can put these in parentheses here. So if you do a custom plot, I would put the % in parentheses. It's a standard procedure. So the component 3 kind of drops off. So it's only 9%. I do like to look at one or two more components just to see if there's anything interesting. But yeah, since we have so few variables, I don't think we need to do it here. So this last line here gives us the cumulative variance. So 86% is explained by the first two components. So this was a very effective way to summarize our data set. In 2 dimensions, we already see 87% of what's going on in our data. And if we wanted to look at the loadings, so those are the correlations of our original variables with the principal components. So for component 1, it's all those. So my component 1 primarily represents murder, assault, and rape. And then the second component here primarily represents urban population. So that's where this correlation is high with the second component. If you want to see this a little bit more clearly, you can modify this comment. You actually see that the loadings are omitted if the values are smaller than 0.1 or something like that. But you can set that cutoff to any value that you want. So if you want to see all the numbers, just put a cutoff here, and you see that's just below 0.1. And let's see, sometimes it actually helps to put a high value here. So we can put 0.5 perhaps, and then only the highest values are shown, right? So you can see that murder, assault, and rape are component 1 and urban population is component 2. And since this already explains almost 90% of our total variation in the data set, then we typically don't need to look at component 3 and 4. Okay, let's look at our second example. That's a climate data set. So if we look at the data table here, it's actually a fairly big data table with thousands and thousands of rows. It's a gridded data set, so it has an X and a Y coordinate, an elevation. It's a spatial data set, GIS data set, and we have an ecosystem here, a mapped ecosystem, and then we have a bunch of climate variables here. So we're working with a rather different data set, but as you will see, you can do some very interesting multivariate statistical analysis also with spatial data. So let's attach this data set to keep our code simple, and we're just going to visualize it. So there's a library lattice that allows me to do a plot of my data set. So it's sort of I'm replacing a GIS system here. And we start with the color ramp. I just want a nice color ramp for my precipitation going from brown to yellow to blue. And so then this is a command. So we are plotting the log of mean annual precipitation as a function of my X and Y coordinates. So my aspect ratio is meters in both axes, so it's the same units. And so if I use 100 colors, I need 99 cuts in my color plot, and my color ramp is this custom precipitation color that I made here. So that allows you to visualize what the data really looks like. So high precipitation is all that's green, and the dry areas are in brown. So just to look at our data in these X and Y coordinates, our UTM coordinates in meters. So let's do the same for temperature, mean annual temperature. You see slightly different patterns. So the warmest area is obviously in the south, then the boreal subarctic up here is quite cold, and intermediate values in central Alberta. So we have something like 15 variables like this in our data set, various aspects, and the goal of our analysis is to see what kind of climate factors are there. How can those climate variables best be summarized? So if you just look at this gigantic data table, that is not very easy to see, and if you flip through dozens of maps for all those different climate variables, that may also not be too insightful. So how can we summarize the climatology of Alberta effectively? So let's run the same principal component analysis, but we have to be a little bit careful. We don't want to run it on our X and Y coordinates. So I'll do this little command here, data frames of names of our data set. So this just numbers my variables. So my climate variables start here with at 6, mean annual temperature, mean warmest month temperature, mean coolest month temperature, and so on. We'll talk about those later, but there's all kinds of climate variables, from dryness indices to growing degree days to precipitation as snow, and so on and so forth. So we want to go from 6 to 18, so those are our climate variables. So that's specified here. And other than that, it's exactly the same analysis as we did above with the US arrests data. So let's run it and do our biplot. And this looks a little bit ugly here. So we don't necessarily want to work with those built-in plot commands. So we customize this a little bit. So instead of using this built-in plot command, let's write out our scores. So those are just the coordinates of all those points here. So we don't want those numbered or anything like that. So let's write them out as a data table. We can look at this. And so this is just all the components, all the principal components for all the rows. And that allows us to do exactly the same plot, but a little bit better customized. So we're working with just the first and second component. We're making our points a little bit smaller, and we give them just a color so that we can see this nicely, and we color it by ecosystem. So sometimes in the latest version of R you have to make that a factor variable. It's not the default anymore. So let's see how that looks. So those are all my grid cells, right? But now displayed on a principal component plot. We can add a legend here with all our ecosystems. We'll actually do a little graphics lab later on today, so you can understand the syntax a little better. Those are the names of my abbreviations of my ecosystem. So red is alpine, and so on. These are all abbreviations. CP is central parkland, and so on. And now we can add our vectors here. And we use something out of the Vegan library. You can use this to put on vectors on all kinds of different plots. And so we first have to fit the vectors. So this calculates the correlations between my component scores here and my climate variables. Remember, these were columns 6 to 18 of my Alberta climate data set. So let's execute this, and we can add those vectors here. And that is a representation of the climatology of Alberta. Over here, we have, for example, high values in precipitation as snow, mean annual precipitation, and those are the alpine and subalpine climates. And then down here, those are the very cold ecosystems that have low values of mean coldest month temperature and mean annual temperature, and so on. And then on this side are the grasslands, the dry ecosystems. Okay, that's already a decent summary. But we can actually do one better. We can map these principal components. And so what we're going to do here, we apply a color ramp to the component 1 and the component 2, and then put them back on the map. So let's say everything that has a negative value of component 1, we're going to make this red and then go to yellow and to green on the other end. And the same we can do for component 2. So if we apply a color ramp on this axis, then everything down here may be red, going to yellow, and then going to green. And each of those little pixels here will color it accordingly, according to those components, and then put it back on the map. So let's see how that looks. And just for reference, let's start by looking at how much variance is explained by our components. So first one, 53, second one, 33, component 3 is 7%. So it looks like we should look at the first two components. That effectively summarizes almost everything. And then the third component, I like to look at one more, see if there's anything interesting going on. So sometimes there can be something. So I like to generally look at one or two more than I have to, just to be sure that I don't miss anything interesting. Let's look at our loadings. And I set the cutoff here to 0.35 so that we don't see all the components. So there are my components, and I can see the first one actually is loading high in warmest month temperature and degree day 5. So this is all about summer temperatures. So let's look at our component. So I'm just coloring this now with the green to yellow to red color ramp. And there it is. Let's go scroll back up here to our loadings. So whenever the values are high, in the red we have warm summer temperatures and long degree days. So growing season degree days, that represents time that plants can grow well. Okay, so that's our first component. The mountains are excluded, also the highlands here are excluded, but it is quite red all the way to the top of Alberta, so there are actually agricultural areas all the way up here. It's far north, but you also have those long days. So this growing season descriptor, that is my first climate component in Alberta. Now let's take a look at the second one here. Let's see how that looks. So that's very different, and that's my second component. And let's take a look at those numbers here. So what does this represent? Mean annual temperature to some degree, and the highest scores here are for coolest month temperature difference. So that's the difference between January and July temperature and degree days below zero. So this indicates particularly harsh winters. So that second component represents a continentality gradient. So we have very continental climate in the far north and toward the east, and then all of the foothills and Rockies are actually quite mild in comparison. So even in the high elevation areas of the Rockies, you don't really get the super harsh Arctic temperatures. So that's a second independent climate component that governs the climatology of Alberta. And now let's look at the third component as well here. Let's scroll back to see what that is. So that's my component 3 here. So that is mean summer precipitation, summer heat moisture index, number of frost-free days, frost-free period. So this is also a growing season component, but it has to do with moisture. So summer moisture conditions are represented by this one here. And that's interesting because it's a band that goes right across Alberta. And that is something that you actually don't see in any individual climate variables, but you see it here in the third component. Even though it doesn't account for too much variance, it's a very interesting one because that's the path of the jet stream in the summer. So the jet stream in winter goes through the US, but in the summer it crosses the Rockies and goes like this diagonally over the province. And the jet stream brings thunderstorms with it. So you have this band of precipitation here, so it meanders a little bit. But that is definitely the third major climatological component that would comprehensively, now we're at 95% of all variances explained, that would so very comprehensively describe the climate of Alberta. So very nice, very effective summary. That is the power of principal component analysis, to reduce complexity like this. And you can use it on all kinds of data sets. So I just got you started here on 2 very, very different examples. So you can see if you can apply this to your own data and your own ideas of what underlying components are in complex data sets.